Hello everyone, welcome to this lecture. So, in this lecture we will continue our discussion regarding the efficient framework for generating the secret sharing of uh, random multiplication triplets, which we started discussing in the last lecture. And in this lecture we will see a triple transformation protocol, which will be useful for instantiating both the components of the above mentioned framework. So, just to quickly recap, the framework requires two protocols. The first protocol is the triple sharing protocol, which allows a dealer to secret share multiplication triples, where if the dealer is honest, then its multiplication triples remain private, unknown to the adversary, and the verifiability guarantees that even if the dealer is corrupt, it has secret shared multiplication triplets and not arbitrary triplets. And the second component, second protocol is the triple extraction protocol, which takes a bunch of random and non-random secret shared multiplication triplets. Namely, there will be a set of multiplication triplets, each of which is secret shared. Some of these multiplication triplets will be known to the adversary, some of the multiplication triplets will be random from the viewpoint of the adversary. The exact identity of the multiplication triplets, which are unknown to the adversary, will be not known. Without knowing which multiplication triplets are unknown for the adversary, this triple extraction procedure helps us to get a bunch of secret shared multiplication triplets, all of which are guaranteed to be random from the viewpoint of the adversary. Now, we want to instantiate this triple sharing protocol and triple extraction protocol, but before going into the instantiation, we have to discuss another protocol called triple transformation protocol, TRIP-trans, which is a common gadget used both for instantiating the triple sharing protocol as well as the triple extraction protocol. And as the name suggests, triple transformation, TRIP-trans. TRIP-trans here stands for triple transformation. What exactly is the transformation? The transformation here is that it takes a bunch of secret shared triples, which may not have any relation among them, and it transforms them, this protocol transforms them into a bunch of secret shared triples which have a correlation. What exactly is the correlation? We will see very soon. So, this triple transformation protocol takes a set of L number of secret shared triplets, where L will be of the form 2D plus 1 and D will be at least T. And I stress that these triplets need not be multiplication triplets. In fact, it could be the case that none of these input triplets is a multiplication triplet, or it could be the case that all but one among these L triplets is a non multiplication triplet. So, it could be any possibility, right, and there is absolutely no relationship among these L triplets. They are just L arbitrary triplets which are secret shared. Now, this triple transformation protocol transforms this input secret shared triplets into output secret shared triplets. So, the number of output triplets is same as the number of input triplets, but now the output triplets are no longer unrelated, they have some correlation among them. Okay. So, before going into the correlation, you can see here that I have used different fonts to represent the input triplets and the output triplets, okay, just to avoid confusion here. So, what is the correlation which exists or which we want among the output triplets? The correlation are the following. we want that at the end of the protocol there should exist 3 polynomials, an A polynomial, a B polynomial and a C polynomial of degree d, d and 2d respectively, such that all the following properties hold. The first property is that all the output A components of the all the A components of the output triplets, they should lie on the A polynomial. So, if I consider the A component of the first output triplet, the A component of the second output triplet and the A component of the nth these are the shares. Sorry, if I take the A component of the first output triplet, the ith component of the A component of the ith output triplet and the A component of the nth output triplet, all of them should lie on my A polynomial, okay, where the degree of the A polynomial is d. In the same way, I require the B component of all the output triplets to lie on the B polynomial. And in the same way, I would like the C component of all the output triplets to lie on the C polynomial. Of course, this output triplets have to be available in the secret shared fashion, where the degree of sharing should be t. Okay. That is the first correlation. The second correlation that we want here is that the C polynomial should be equal to the product of the A and B polynomial if and only if all the input triplets are multiplication triplets. Stated in a different way, what I require here is that if the ith input triplet is a multiplication triplet, then ith output triplet should be a multiplication triplet, and this is an if and only if condition. That means, I want the property to hold in the other direction as well. That means, if the ith output triplet is a multiplication triplet, then the ith input triplet was also a multiplication triplet. That automatically guarantees that if all the input triplets are multiplication triplets, the first, the second, the ith and the nth, then automatically all the output triplets will be multiplication triplets. And as a result of that, since the degrees of A, B and C polynomials are d, d and 2d respectively, it will be automatically guaranteed that the C polynomial is the product of the A polynomial and B polynomial, because the A component of all the output triplets, B components of all the output triplets and C components of all the output triplets, they are distinct points on the A, B and C polynomials respectively. So, that is a very powerful correlationship. So, even if my inputs are arbitrary triplets, I have tied them together through this triple transformation process by ensuring that I transform the input triplets into output triplets in such a way that the output triplets now constitute distinct points on the A, B and C polynomials. However, you see the degrees of the A and B polynomial are d, whereas the degree of the C polynomial is 2d, and The second correlation that I want here is that if all the input triplets are multiplication triplets, then all the output triplets will be multiplication triplets, and that will further guarantee that the C polynomial will be the product of A and B polynomial. However, if any of the input triplet is not a multiplication triplet, then the C polynomial will not be the product of A and B polynomial. Say for instance, the ith triplet is not a multiplication triplet, then the ith output triplet should also not be a multiplication triplet, and since the ith output triplet constitute distinct points on the A, B and C polynomial, we know now that there is at least one point on the A, B and C polynomial which violates this multiplicative relationship. So, that is the second correlation which we require from the triple transformation protocol. And the third property which we require from the triple transformation protocol is that if the ith input triplet was random for the adversary, of course, adversary will be knowing T shares for all the input triplets as well as for the output triplets, because everything here is secret shared. But it could be possible that the ith input triplet was random for the adversary, it only knows T shares for the ith input triplet. If that is the case, then we would require that the privacy for the ith output triplet is also maintained. That is the third requirement. So, that these are the three properties we require from the triple transformation protocol. Later on we will see that assuming we have this triple transformation protocol, how we can instantiate the two components of our efficient framework for the pre-processing phase protocol. So, now we will see in this lecture how to instantiate the triple transformation protocol. Before going into the instantiation of the triple transformation protocol, for the purpose of representation, I will introduce here a notation for representing Samir secret shared values. So, imagine there is a value S from the field which is secret shared as per the Samir secret sharing scheme through a T degree polynomial, with every party holding a share for this secret. That means there exists some T degree polynomial whose constant term is S, and ith party holds the value of the Samir sharing polynomial at alpha I. If that is the setting, then to represent that setting I will use this box representation. Okay. Why this box representation? This box representation basically signifies here that there is a value S which none of the party knows. Of course, the dealer who would have secret shared the value S would know the value S, but if the dealer is honest, then from the viewpoint of the corrupt parties, there is a value in this box which is not known to the adversary. Adversary has only T shares for the value which is kept inside the box. And we will also use this notation, this square bracket S with subscript T to denote the vector of shares corresponding to a secret sharing of S. Now, we already know the linearity property of Samir secret sharing. So, we know that if there is some publicly known linear function g over the field, and if the inputs for this function g are secret shared as per Samir secret sharing, then without any interaction the parties can locally compute their respective shares corresponding to the output of the function g. So, that will be represented pictorially by the following representation. So, you have now the inputs for this function g in the box representation. That means, for x 1 each party has its share, for x 2 each party has its share, for x l each party has its share, and now the parties can locally apply the function g on its respective share of x 1, x 2, x l, which will help every party to obtain its share for y 1, y 2, y m, namely the output for the function g. So, this whole process I will pictorially represent like this, and I will also use statements like parties locally compute the output of the function g by writing this expression. So, whenever I write this expression, that means I want to say that every party pi, every honest party, to be more specific, because corrupt party, a maliciously corrupt party pi may not follow protocol instructions, but every honest party pi, it takes its shares of x 1, x 2, x l corresponding to the secret sharing of x 1 to x l, applies the function g and gets its shares corresponding to y 1, y 2, y m. That is what I mean whenever I write this expression. Okay. So, now coming to the triple transformation protocol. So, this is your input. What exactly is the input here? The input is a bunch of L number of secret shared triplets. They need not be multiplication triplets, I stress here, where L is equal to 2t plus 1 and d is greater than equal to t, and there may not exist any correlation among these secret shared triplets. Now, the steps of the triple transformation protocol are the following. The first d plus 1, for the first d plus 1 output triplets, we set the A component to be the same as the input itself. So, I take for I equal to d plus 1 the A component of the input triplets, and I consider those triplets to be the first d plus 1 output triplets. So, it is basically just renaming, that nothing else. So, whatever the shares for the first d plus 1 triplets parties have, they focus on the shares corresponding to the A components, and those shares are only considered as the shares corresponding to the A component of the first d plus 1 output triplets. Okay. So, in terms of box representation, you can imagine that whatever shares the parties have for this A 1, namely the A component of the first triplet, those shares are retained as the shares for the A component of the first output triplets, and like that whatever shares parties have for the d plus, for the A component of the d plus 1th input triplet, those shares only are retained as the shares for the A component of the d plus 1th output triplets. Now, the A polynomial is defined to be the unique d degree polynomial passing through the d plus 1 distinct points which are written down here. Namely, we assume that let A be the d degree polynomial over which the first d plus 1 A component of the output, over which the A component of the first d plus 1 output triplets lie. And this A polynomial is a well defined polynomial. Why it is a well defined polynomial? Because its degree is d. So, any d degree polynomial can be uniquely defined if I set or if I fix d plus 1 points on that polynomial. So, what are the d plus 1 points which I have fixed for the A polynomial? Those points are basically the A components of the first output triplets, which are actually the same as the A components for the first d plus 1 input triplets. I stress here that no one will know the value of this A polynomial. That means, none of the coefficients of A here is known to anyone, because the points on this A polynomial, namely the A component of the first triplet, the A component of the second triplet, the A component of the d plus 1th output triplet, all of them are secret shared. As a result of that, the coefficients of the polynomial A are also secret shared here. Okay. So, this is the way I have set my A polynomial, and now I know that if I want to compute some new points on this A polynomial, namely the value of the polynomial at alpha d plus 2, the value of the A polynomial at alpha of d plus 3 and the value of the A polynomial at alpha of 2 d plus 1, then these values are linear function of the first d plus 1 points on my A polynomial. And this linear function is publicly known, namely it is the Lagrange interpolation function. And we know that secret sharing satisfies the linearity property. So, we already have the secret sharing of the first point on the A polynomial, we already have the secret sharing of the second point on the A polynomial, and we already have the secret sharing of the d plus 1th point on the A polynomial. So, if I apply this linear function on those secret sharing, then that will enable us to get the secret sharing of the next points on the same A polynomial without doing any operation. So, as a result we can say that the parties now locally compute the A component of the remaining output triplets. Okay. That simply requires applying linear function. So, you have fixed the A polynomial here in a secret shared fashion, apply the linear function and get this done. That is how the input, that is how the A component of the input triplets are transformed into the A components of the output triplets. The same process we do even for the B components of the triplet, namely we take the first d plus 1, we take the B component of the first d plus 1 triplets, each of which is secret shared, and we define and we consider them to be the B component of the first d plus 1 output triplets, and then we define the unique d degree B polynomial passing through the B component of the first d plus 1 output triplets. And then we can apply the Lagrange linear function and get the next bunch of points on this defined B polynomial. Since everything is now linear function, that linear function can be now applied on the secret sharing of the points on the B polynomial, and we can get the transformed P components for the output triplets. Okay. So, our A polynomial is defined, our B polynomial is defined. Now, our goal is to define the C polynomial. Now, you might be tempting to do the following. You might say that why we are anyhow given 2d plus 1 number of secret shared C components. Why can't I define the C polynomial to be the following, that let C to be the 2d degree unique polynomial, which when evaluated at alpha 1 gives you the C component of the first triplet, when evaluated at alpha I gives you the C component of the ith triplet, and when evaluated at alpha of 2d plus 1 gives you the C component of the last input triplet. If I do this, then you will say that okay, I have now an A polynomial of degree d, B polynomial of degree d and C polynomial of degree 2d, fine. One of the requirements of the triple transformation protocol is achieved. But if I define my C polynomial like this, then it is not guaranteed that the C polynomial is the product of the A polynomial and B polynomial if all the input triplets are multiplication triplets. No, because if you see here, the way I have defined the A polynomial and B polynomial is as follows. The A polynomial is defined by fixing the first d plus 1 points here. They are basically the first, they are basically the A components of the first d plus 1 input triplets, but the remaining points on the A polynomial they are not the same as the A components of the remaining input triplets. They are basically now new points on the A polynomial. In the same way, the B polynomial is defined by fixing or by setting the first d plus 1 points to be the B components of the first d plus 1 triplets, but the next bunch of d points on the B polynomial, they are absolutely different from the B component of the remaining input triplets. But for the C polynomial, I am taking all the points on the C polynomial to be the C components of all the input triplets. So, what can go wrong here is that for the first d plus 1 values, C polynomial evaluated at alpha I will be same as the A polynomial evaluated at alpha I times B polynomial evaluated at alpha I if the first d plus 1 triplets are multiplication triplets, fine. But for the remaining d alpha values, C of alpha I may not be equal to the product of A of alpha I and B of alpha I, because the next bunch of points on the A and B polynomials, they are absolutely different. Well, they are not absolutely different, they may be different from the A and B components of the remaining d number of input triplets. So, that is why we cannot define the C polynomial like this. We have to do something else to ensure that the second property which we require from the transformation is achieved. So, how do we define the C polynomial? So, we partially define the C polynomial first by fixing the d plus 1 points on the C polynomial to be the C components on the by fixing the first d plus 1 points on the C polynomial to be the C components of the first d plus 1 input triplets, as we have done for the A and B polynomial. Okay. And now, what I do here is that for the so right now I have only d plus 1 points on the C polynomial fixed, but I want the C polynomial to be a 2d degree polynomial. So, to define a 2d degree polynomial, I need d more points on the C polynomial, such that those points should be the product of the A components and the B components of the output triplet if the A component and the B component and the C component were constituting a multiplication triplet. So, how do I do that? So, for that, for the remaining d points on the C polynomial, I obtain them by computing a secret sharing of the product of the A and B component by using the input triplets which I have not yet touched, and for that I apply the Beaver's method. So, what was the Beaver's method? So, remember Beaver's method helps you to do the following. If you have a multiplication gate, say x and y, and you want to compute x dot y, and if you have an auxiliary secret shared say A B C in the pre-processing phase, or somehow you have got that secret shared triplet A B C, then we would have publicly computed x minus a, we would have publicly computed y minus b, and then we would have expressed the product of x and y as a linear function of secret shared A B C. That was the Beaver's method for computing the secret sharing of x times y. What we are proposing here is to compute a secret sharing of the product of the A and B components of the last d output triplets by using the d number of secret shared triplets, input secret shared triplets which we have not yet touched. So, remember throughout this process of defining the A polynomial, B polynomial, we have not touched the last d number of input secret shared triplets. We are now going to utilize them for computing the remaining points on my C polynomial. So, what we will do now is the following. So, for instance, we take this pair of values which are points on my A and B polynomial, and now I want to compute a secret sharing of A times now I want to compute a secret sharing of this value. For that I will apply the Beaver's method using this as my auxiliary triplet. So, I will perform this operation and that will help me to give a secret sharing of a output value which will be T shared, and then I will simply ignore this input triplet. Like that I will take this pair of values and I will take the last secret shared input triplet, apply the Beaver's method, and then I will get a secret sharing of this value. And now I have 2d plus 1 number of secret shared C points using which I will define my C polynomial. So, you can see the process of defining the C polynomial is different from the process of defining the A and B polynomials. The A polynomials, for defining the A and B polynomial, we do not need any interaction whatsoever. First fix the d plus 1 points and extend them non-interactively to get the remaining points. Do the same thing for the B polynomial. For the C polynomial, half of the points, in fact more than half of the points are fixed, and then the remaining points are computed interactively by applying the Beaver's method using the input triplets, the last d number of secret shared input triplets as the auxiliary triplets. Okay. So, that is the triple transformation process. In the next lecture, we will discuss the properties achieved by our triple transformation process. Thank you.